Not sure why it doesn't work. Okay, I think I'm live on Twitch as well. What the hell? Okay. I think we can start finally. I should be streaming on both YouTube and Twitch right now. Okay. I also should test if my mic works, because I got a new mic. Or mic. I think I'm very quiet. I'm not sure why. Okay, I'm gonna test it now. Okay, I'm gonna test it now. Okay, this is pretty good now. Alright. I could even go all the way up, I think. Okay, this is pretty good now. Alright. I could even go all the way up, I think. Okay. So yeah. Okay. SGD. Well, he did a simplification here with linear methods. So it assumes that x of s, which is the features thing, vector, I think it was. It's been a while since, it's been a few days. Let me leave this. Okay. I think last time, yeah, that's where I was stuck, the proof. Okay. So, linear methods. Real valued vector x of s with the same number of components as w. So each weight has a corresponding what does he mean by x1, x2, x2? Okay. The inner product between w and x of s, which is still a vector, okay, is the transpose, because this is a column vector, now it's a row vector. Dot product between the row vector and the column vector. So it's just the sum. Okay. Linear in the weights. The vector is called a feature vector. Sorry for the yawning, I'm pretty tired. Each component the vector x of s is called a feature vector representing state s. Each component of this vector is the value of a function. So basically it's just saying that, again, each one of those is also a function. Oh, okay. Each one of the component of the vector is a function. So that, okay, so x okay. So x is a function which maps each state to a vector of functions that maps the state to a value. Basically, that's what feature vector is. X of s, the x function, basically. I guess we can call it the feature function. In its domain has states, and in its I forgot what it's called. Image, was it? I think. Anyway, it maps states to vectors of functions that map states to values. That's basically what he's saying here. We think of a feature as the entirety of one of these functions. So, okay, so we call this function a feature. So a feature okay. I'm not sure what he's referring to as a feature here, the x function or the component of the f. I think it's the x function. So a feature is a mapping between states and vectors of functions that map states to values. And then and then okay, and then x of s, which is a vector, is a feature of s. For linear methods, features are basis functions. Basically means that they're not redundant, so you cannot simplify them, nor can you write one as the other in terms of the other. And when you compose them, you can represent any function in the set that you're interested in. Constructing d-dimensional feature vectors to represent states is the same as selecting a set of d-basis functions. Features may be defined in many different ways. We cover a few possibilities in the next section. It is natural to use SGD updates with linear function approximation. Gradient of the approximate value function with respect to W in this case is the feature vector. Thus, in the linear case, the general SGD update reduces to a particularly simple form. The feature vector. That looks really bad though, because then you just have okay, let's see how that goes. Okay. So this part is important. Basically, this is the weight, this is the next calculated weight. I mean, these are the weights, and this is these are the next calculated weights. This is the learning rate, the immediate reward, discount factor, transposed weight matrix, feature vector, but the next one, how does that work? This is the feature vector of the succeeding state. Yeah, because this is the shorthand. So the feature vector of the succeeding state times the weight of vector minus of the current one. And that times this. Okay, that's a bit confusing. And then here he rearranges that to be this. The reward times the current feature vector or feature of S. I think that was the language. Feature of S, right? So feature of S, okay, so the immediate reward times the feature of the current state minus the feature of the current state times the feature of the current state minus the discount of the feature of the next state. Okay, I don't get this. I'll have to ask my good old friend ChatGPT. In particular, I just care about this part. So basically plain always intuitively. The difference between the TDR, okay. The difference between the new estimate and the current prediction. How come the multiplication or the dot product great question. He's always very uplifting. Vector of weights. These are the parameters I'm learning. Okay, I know that. This is feature vector presenting the state S. The weighted sum of the features, a linear combination. In function approximation, you're assuming that the value of a state S can be estimated as. I'm pretty sure this is only in the linear case. I don't think you can do this in any other case. Okay. So the aspects, as you call them, or subdivisions, actually that's too fancy, or parts of a state, and then the state, and then the weights which tell how important the state is, give us prediction. Is prediction here basically value that tells us how good it is for us got it. The prediction is the estimated value of being in that state. Good means expected future rewards, the return. Okay, so the TD update then again is this. So this gives us the V of S T plus, okay, this is basically our TD update rule is the immediate reward. I know you guys don't see this, but there's not many people watching anyway, so if there are later on, I will also get a way to try to stream my phone screen while I'm drawing stuff. So okay, let me just close the balcony, it's pretty cool. So I just want to get around to try to implement this All right. The immediate reward, so our TD error for the current timestamp is the immediate reward plus gamma. And now I define V of STW to be equal to, I don't know why he didn't give that definition. I'm gonna ask that to ChatGPT right now. But I think this is right. I think this is entirely correct. Xt plus 1 given xt equals x of s of t. Okay, so this is what I sketched up. Equals w sub t, and then the, how do you say that, the transpose of that. Transpose. Okay. Time. Well, times, I guess. It's not really, it's dots. X sub t plus 1 so is it correct to say that where x sub t equals x of s sub t and v is the estimate of the value for function? You're very close. That's, oh. Ah, okay, yeah. That makes sense. I don't know why I wrote that. What? Yeah, but I can update the weights. No. Oh, so you get the next state's estimate, but only as good as the current weight vector can estimate. I broke ChatGPT with my questions. We got exactly one person watching, and that's me. Exactly, that's a key insight. You're saying, given what I currently believe, how good is the next state likely to be? So, my TD error for the current timestamp t is basically the current reward I just got taking into account two things: current reward I just got and the difference between the current state estimate and the next state estimate, using the knowledge I currently have weights. Yes, fire, that's exactly it, beautifully said. Okay. Oh, I forgot to mention the discount. Okay. Gamma. I thought ST was worth... Wow, I'm impressed by ChatGPT here. Wow, okay. So I thought S sub t was worth this much. Then I got a reward. And I now think the next state is worth this much. So maybe S sub t is worth more or less than I originally thought, depending on the reward. Oops, I underestimated or overestimated how good that state was. Let's just adjust my thinking just a bit. You nudge the weights in the directions of x sub t. Ah, okay. So here, if the reward is not so high, and the next state is a low estimate, a TD error may be a negative number, which would then result in decreasing respective weights, right? Well, actually, I don't actually understand this. Wait, that's really smart. So then what happens is that this particular feature becomes less important because the respective weight decreases, right? Yes, exactly. Okay. Just here, mathematically, okay, this is a constant, doesn't matter. This is a feature vector. It's a column vector. This is a column vector. This is some number, which would then be multiplied by each of the... What I don't get here is Oh, my feet are cold. Gotta wear socks. Yes, you're adding a scaled version of x sub t to the weights, but what matters is that the TD error can be positive, 0, or negative. That's true. If it's negative, then I mean, if it's 0, then everything will be 0. You're subtracting from the weights. You're adding to the weights. It's not always adding. The update and direction TD error. Wait a sec. But that doesn't make sense. Wait a second. TD error is not a vector. Meaning, if one of the features is over as valued, or one of the weights is overestimated, that means all weights will be updated. No? That's what I understand from that. What the fuck? Oh, that's why. That is the reason why it's better than tabular methods, because you're updating all state, like all. Okay. And tricky, you nailed it. Okay, it's capital YES, fire. You're totally right. Let's go deeper. Magnifier. TD error is a scalar. The scalar error is then used to scale the entire feature vector, and this whole product is added to W sub t. Even if only one feature, say x sub t and then subscript 3, I don't even know what that is, superscript 3, is responsible for the overestimation, the TD error is blamed on the whole prediction, not on any individual feature. So all active features get updated, even if they weren't at fault. That's because linear TD learning doesn't have any way of knowing which individual feature caused the error. So yes, this is both a strength and a limitation. It keeps the algorithm simple and efficient, and works well when features are cleanly informative. It can blame the wrong feature, especially when features are correlated or poorly designed. Good feature engineering matters. More complex methods sometimes help when you want to assign credit more precisely. Yes, scalar. Well then, features need to be disjoint. Ideally, at least. Boom, you're on fire right now. That's an excellent and super deep. Okay. Yes, in an ideal world, disjoint or uncorrelated features are much better for learning with TD and linear function approximation. But oh, I love this song. Megalomani. No, it's Clownomania. First time chat. This guy's advertising himself in my chat. Reports. Spamming and advert. advertising in the chat. Send warning. Unable to. Okay, great. I think most of my viewers are from the US, if I'm not mistaken. And everybody's asleep in the US right now. So, yeah. Yeah, United States, India, UK. That's basically who's watching my streams. But most from United States and India. Okay, actually it's not too late in India right now. It's kind of like 4:30 p.m., 5:30 p.m. I think India time now. It's 6 p.m. Okay, anyway. So can't I delete this? Okay, it doesn't matter. Is this the case with cannons? Why do all AI guys prefer to talk in such a loser way? Just tell me what happens. There is no such thing as disentanglement in maths, nor are there hidden layers. I'm not explaining this to a 3-year-old. That seems like magic. I don't understand that. Okay. Let's continue. I don't know why he chose to do this here. This is much simpler to me than this, but okay. This is the difference in the features transpose times the features times the weights. Doesn't make much sense to me. Though it does make sense, yeah. Okay. Wow. Isn't that I know what's a diagonal matrix. I know what this is, of course. Okay. Identity matrix is just all ones, right? Sorry, no. Oh yeah. So an identity matrix is a diagonal matrix. Okay. So what he's saying is, if any of the diagonal elements are negative, so we got I here, 1, 1, 1, and then all zeros, and then a diagonal matrix. If any of the diagonal elements are negative, then the corresponding diagonal element will be greater than 1. Okay, that's actually much simpler than I thought. Okay, that's true. It's just, how can you write it as that? We got 9, 10, right? Let's first get that straight. So okay. I'm just gonna change the music because I'm bored. So he's rewriting that as the problem is I forgot. I mean, that's alpha. That's W sub t plus alpha b plus alpha a wt. And then I can say that equals W sub t of one, actually, plus alpha a. Plus alpha b. So how is 1 plus alpha a the same as 1 minus alpha a? I mean I minus. What? Let's see that. How can he rewrite it? Oh, sorry. I just wrote it incorrectly. Yeah, I just wrote this incorrectly. This is a minus, not a plus. Okay. Yeah. Here when you take this to WT, what you get is 1 minus alpha a wt plus alpha b. And 1 is the same thing as I, because when you multiply any matrix with the identity matrix, you get the same matrix. Okay, yeah, he's right. And you get identity matrix here. I forgot what it's called, but constant multiplicative or some shit. Okay, thank you. Multiplicative neutral element, that is. Okay. Okay, at least I understand now this. And then what he's saying is if any of the diagonal elements are negative, then that will surely be positive, which means that which will lead to okay, will be greater than 1, and the corresponding component will be amplified, which will lead to divergence if continued. On the other hand, if the diagonal elements are all positive, then alpha can be chosen smaller than 1 over the largest of them, such that is diagonal with all diagonal elements between 0 and 1. I don't get what the fuck that means. Absolutely don't understand. I'm not gonna try to even understand that. Sorry. Oh, come on, man. Well, what does this mean? Okay. Okay. So if the diagonal elements of A are all positive, then alpha can be chosen smaller than 1 over the largest of them. Can be chosen smaller than 1 over. I don't even know what that means. Like that. That literally doesn't make sense. You can choose A to be less than the reciprocal of the largest diagonal element of A. Okay, that's what I choose A to be smaller than finally. Well, these people are, I don't know why they talk this way. Okay. Ah. Okay, I see what he means here. Oh, then 1 over the largest of them. 1 over. Okay. Well, I mean, that's a topic on its own. Okay. Positive definite matrix. Emory University. All the eigenvalues of any symmetric matrix are real. This section is about the case in which the eigenvalues are positive. These matrices, which arise when an optimization problem are encountered, okay. 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 So yeah, I think I'm gonna end the stream. Not much did I understand from this explanation. I think I'm gonna try to implement this later on. Actually, I want to see this. Oh, I see. By the way, I understand this equation right now. It's just n step. Yeah. I actually skipped this n step bootstrapping, but it makes a lot of sense. Okay, I just have to basically I have to implement this n-step semi-gradient TD. which is reasonably possible. Yeah, actually, let's try to do that. Well, let's see that. I'll call it n semi-gradient I don't get this though, one sec. If you look at the... One sec. It's not here, it's like here. And here. Yeah, TD, right? Oh, okay. Never mind then. Loop for each episode. Loop for each step of the episode. T is infinite. Okay, that's a little more complicated than the previous method. So you reset, so that's looping from each episode. Then what you do is you step through this episode and then you take an action according to the stochastic policy of that state. Stochastic policy is distribution to that state. You absorb and sort an extra word in the next state. If the next state is terminal, then you say that t equals that terminal state. You then have some other t for some reason. You have 3 different t's in this whole thing. It's so annoying. It's so annoying how these people always choose the worst possible symbols known to mankind and the most ambiguous ones to explain their formulas. There's like 6 different t's that just have a different curve on the left side. How the fuck am I supposed to... Okay, this is a capital T. This is lowercase t, and then this is italic t, I guess you can call it. Okay. Italic t equals lowercase t minus n plus 1. This is the time whose state's estimate is being updated. If that time what is he trying to say here? I don't get it, man. I genuinely don't understand what he's trying to tell us here. Oh. Start a new episode, initialize the... Okay, this is just reset the environment. Take action based on policy, store. If next state is terminal, store at this t. Compute the update time. This is time for which we know we now have enough info to compute the end step return. Oh, I forgot this is the end step thing. Okay, it makes sense. T minus n plus 1. Basically, t needs to equal, sorry, n needs to equal t plus 1. Basically, if you want to compute 5 steps ahead, you're supposed to be at least the 4th time step, because you start from 0, I think. I may not be right there, but yeah, okay. My biggest problem is not knowing end step bootstrapping. Okay, let's ask him, sure. Okay. Okay. I think this is really challenging to implement actually, compared to the other methods. What exactly is this stupid, weird fucking P represent? Not that T, since the author decided to, probably on purpose, confuse everyone. There are 3 different fucking T's. The italic one. Tau. No, it is the tau. No, I was talking about the tau, whatever the fuck that is. I don't know fucking Greek, why should I know Greek? Okay, he's trying to make me feel better. What? I don't think it's one of the most understood things in RL. What is he talking about? Okay. Okay, that makes a lot of sense. So okay, so this basically, this you don't even need to define this. It's only defined as infinity because I don't know why. Because of this branching. Okay. Okay. So t, it's 0. It's just the current time step. Take an action, observe, and the next state. Okay. If the state is terminal, then t equals t plus 1. Okay. Not sure why. Ah, okay, that's just used there. No, actually, it's used here too. That's perfect. Anyway, forget about that. Tau equals t minus. That sounds very Asian. Doesn't sound Greek. Anyway, tau equals. It equals t minus n plus 1, because if n is 1 and t is 0, zero minus 1 plus 1 is 0, right? Because then you would already have observed a reward. Yeah, but if you set n as 2, you have to wait for 2 turns. So when t is 1, oh, wow, that's a good transition in the music. So t t0 here. Okay. If you have enough observed, let's say n is 1. That's the simplest case. If n is 1, that equals t. So it's 0. That is 1. What the fuck? Okay. I always get confused with this index manipulation that they do. I'm just not used to it. So this means when you have two numbers, right, A and B, so let's say 5 and 2, 5 minus 2 plus 1 is basically how many numbers there are between 5 and 2, including 5 and 2. So it's 5, 4, 3, 2. That's 4 numbers. We do the exact same thing here, only the negative of that. So that's like how many steps are left. Oh, okay. This could be 0, I think, though. Like equal to 0. So if I do n step 5, right? I'm gonna take an action. I'm gonna observe that. I'm gonna say, is it terminal? It's not terminal. I'm gonna say 0 minus 5 plus 1, which is minus 4. Zero, 1, 2, 3, 4, 5. Well, basically this is... No. This is basically the negative of... Okay. So if you have like a 5 and a 2, you want to know how many more are left from 2 to 5. But this gives you the negative. So I have t equals to 0, n equals to 5. I need to go 4 more steps because I've already taken 1. That's why this +1 is here. Like, I've already observed one thing. It's basically how many... This is basically how many rewards have you observed so far. That's it. Nothing complicated. So it's like you've observed 1 so far. Sorry, no. It's how many more you have to observe to be able to... Yeah. So I've observed 1. I need to observe 5. I don't know why this is just not... Because then wouldn't work in the other way. Yeah, okay. Now it's... I've observed 1. I need to observe 5. I have 4 to go. So it's -4. Nada... Until this guy equals t minus 1. T is infinite now, so nothing there. This goes on for 1, 2, 3, 4. So from 0 to 1, 1 to 2, 2 to 3, 3 to 4. And then when it's at 4, 4 plus 1 minus 5 is actually 0. So I've already taken... Well, if you... Look. I mean, very simply, S0 R A R1 S1 A R2 0 1 S2 A R3 2 S3 A R4 3 S4 it's R5. So it's 1 2 3 4 5 things that I've observed. It's very simple because t starts from 0 and the words start from 1. So once t is 0, and let's say there's 7 states in total. Once t is 0, currently we're at the 4th state. Once t is 0, once tau is 0, g is then equal to tau plus 1. So it's not taking the initials for some reason. Ah, sorry. Rewards don't start from 0. There is no R0. That's why. That's as simple as that. Okay, let's see that. One sec. One sec. Okay. I think the best way to understand this is to just trace it. So t here is 4. This weird t is 0, n is 5. Right? Now I go and collect from 0 until 5. Sorry, from 1 till 5. So it's 1, 2, 3, 4, 5. It's basically t plus 1. This goes until t plus 1, always. There's always an extra state compared to how many rewards there are. That's true. So tau will always be the index at which the state is. Oh, tau is the time whose state's estimate is being updated. And then you just start from the next one until the last state, but then in between there's like n rewards basically. Okay. It can be truncated by, yeah, basically it's like a modulo. I mean, if there's 27 time steps and your n is 5, the last one will go from 25 to 27 because of the min on the upper boundary. And then the discount rate is basically at the last step is going to be n minus 1 basically, right? It will be n minus 1 because that guy also starts from 0, because the first one you never discount and then the last one you discount the most. But if this, so okay, hold up. So you take all of these rewards just fine. In fact, until then, right? And wait. Okay, I was just taking a look at my streams, but yeah, okay. And then, so you had like, okay, I'm gonna draw here so that you draw IO, is it? Actually, no, it's just online paint, right? That's all I need. So this is what I was trying to basically. So now your T is, oh my god, it's so fun. Your T is 4, N is 5, tau is 0. And then you have something like S0, R1, A. Yeah, but I don't care about A here. R1, S1, R2, S2, R3, S3, R4, and S4, R5, and this is exactly where we stop. So when T is 4, which is here, you observe S5, R5 here, and then you stop because because tau becomes 0 here, and then you do actually go from tau plus 1, which is 1, until tau plus n, which is 5, from 1 to 5, and you take each one of these guys and you sum them with the discount rate. And then you say if this guy is basically the if it's basically the last reward, right? Because if S5 comes here, then T equals 5. That means that's it. No more rewards. Then we don't do that. Only if it's less. Only if it continues here. Blah blah blah. Do we do that? No, I just want to... My god. Okay, that's nice. Okay. So... So then we take this guy and we say update this G, and G, by the way, is already the sum from 1 to 5 of I equals Ry. Okay, and then you say G is plus equal gamma n, which by the way was already not applied. It was not applied. Okay, gamma of n basically means the next one, because it's and then the estimate of s tau plus n, so that's this guy w. Wait, I don't understand one thing though. Why do I then update him ever? Should this not be +1? I gotta talk with this guy a little bit. Wait. Please cut the crap. No emojis, no uplifting words, just straight facts to help me understand. Okay. That is definitely not my fucking claim. Read my fucking claim again. ChatGPT will hate me. This is painful. Wait. Can I download this? Okay, it's fine. No. Here I want a new thing. Thank you. Close this up. -1? What? I don't get that, man. Plus ChatGPT isn't even working. Oh, yeah, I'm sorry. Yeah, that's not, that's just continuing the bootstrapping from there on. Yeah, you see here. So we actually do that, yeah. Okay. And then what we do is look, so basically the reward, the estimate, the reward, the estimate, the bootstrapped estimate, that minus the current estimate. Why? Okay. Okay. So then what's the point? Okay. Okay, I need to implement that now. I understand it now. It's not complicated at all. The gradient. Also, there was this thing that says the gradient in linear approximation equals. Okay. But this is no longer GPI though, because when does this even terminate at this point? This terminates if it's t minus 1. Yeah. That means that t minus n plus 1 equals to t minus 1, which means that t minus 2 plus n, the timestamp needs to equal to the last timestamp minus 2 timestamps plus that. Oh, I was talking. If n equals 1, so if it's td0, this basically means until timestamp equals the one before the terminal one. Why? Because you cannot observe anything in the terminal one. Like, suppose you go to the terminal one, what are you gonna do? There's nothing useful. Okay. That makes a lot of sense. So, that's it. I just need to implement this now. Yeah, that's what I was gonna say. This is not GPI. I mean, even if it is, it's not my GPI. I don't know how to fit that inside of this policy evaluation. And then if policy is stable, has nothing to do with policy evaluation actually. Wait a second, this is I don't even update the policy here. I just learned the weights. Okay, I need to ask that to ChatGPT. It's a bit confusing. Wait a second, I will tell ChatGPT. Wait a second. I am not learning either the value function nor the Q function, nor yet the policy here. I am just learning the weights. So how am I to use that to then greedily behave with respect to the weights? This is important. Oh my god. So this is just the evaluation part of the GPI. So this is not a substitute to TD0 tabular methods, since TD0 is a complete algorithm that learns the agent uses and learns. Okay. Okay, so this is a... Wait, what? Okay. Okay, I'll take a look at this article. But I think I'm gonna close the stream now. I streamed for like 2 hours and 46 minutes. That's not bad. That's okay. That's reasonably fine. So, yeah. Okay. So the continuation of this will be to read this article by Michael O'Neill to try to understand how this fits in the control algorithm. But I think it should be very simple. In fact, I actually think that it's exactly the same as this TD. Wait, let me see that. Wait, can't I use the exact same code, which works by the way, that I have now, and just incorporate function approx here by changing the update rule to instead use function approximation, i.e. weights and features versus instead of Q function. Okay, we'll continue later.